Let's move on to the next problem. A motorboat starting from rest on a lake accelerates in a straight line at a constant rate of 3 meters per second for 8 seconds. How far does the boat travel during this time? Right. So we have three things here. We have the motorboat starts from rest, which means that the initial velocity u is 0. The acceleration is 3 meters per second, and the time taken is 8 seconds. So we can use the second equation of motion, which is s, to calculate the total distance or the displacement here. S is ut plus half at square, right? So u is 0, so the first part becomes 0, and it's half of the acceleration is 3, and the time is 8, so which is 64. And which means that the total distance through this calculation will get you to 96 meters. So let's go to the next question. A driver of a car traveling at 52 kilometers per hour applies brakes and accelerates uniformly in the opposite direction. The car stops in 5 seconds. Another driver going at 3 kilometers per hour in another car applies his brakes slowly and stops in 10 seconds. On the same graph, plot the speed versus time graphs for the two cars. Which of the two cars travel farther after the brakes were applied? Okay. So we have the scenario of two cars. The first car was traveling at a speed of the u of the first car is the initial velocity was initial speed was 52 kilometers per hour. For the second car, the initial velocity was 3 kilometers per hour. Now, so we have two problems to solve, and which for the first car, the initial velocity is u, and here we are converting that into meters per second, which means that you'll multiply them by 1000 in the numerator, and you'll divide them by 3600, right? So with this, and you have the first car took 5 seconds to come to a complete halt, which means the final velocity is 0. And with this, you can calculate the acceleration of this car, which is we can use the first equation here, which is your final velocity is 0, so v is equal to u plus at, and with that you see that your acceleration is going to be 2.9. And with this, with the acceleration, you can also find the total distance, which is going to be your ut plus at square, right? Your total distance is equal to ut. U is 14.4 times 5 seconds plus half of acceleration is 2.9 times time is 5 square, which is 25. So we see that the total distance, it had to travel a distance of 108.25 meters before coming to a complete halt. This is the first car. If you apply the same logic for the second car, taking u as 3 kilometers per second and calculating its acceleration comes down to 0.83 meters per second, and using that acceleration, if you calculate the total distance, it comes down to be 12.45, right, is the distance. Now, if I'm going to plot this whole thing in a graph, if you see here, the first car was traveling at a higher speed, right? Basically, this line talks about the graph of the first car. It traveled somewhere, the velocity was pretty high, of around 52 meters per hour, and then it came to a complete halt in 5 seconds. So when the time was 5, it came to a complete halt. That's where it hits the exact the point is here is 0. The value of velocity is 0 here. However, the second car started with 3 kilometers. Sorry, it's not. This should not be 0.83. This is the velocity, right? The second car started with 3 kilometers per hour, and when it came to a complete halt after 10 seconds, it took longer time to come to a complete halt. Here. So the graph is going to look somewhat like this. Here, the initial velocity was low, and it took a longer time to come to a complete halt, and this one came to halt pretty quickly in 5 seconds. Right. So this is how the graph would look. And to answer the second part, which of the two cars traveled farther after the brakes were applied? We saw that the first car traveled a distance of 108 meters to come to a halt, while the second car traveled 12.45 meters to come to a complete halt. So which means that the first car traveled farther when the brakes were applied. So the sixth question is find the figure. This figure shows the distance time graph of three objects A, B, and C. Study the graph and answer the following questions. Right. So this is a distance time graph. So which means that for every unit time, this captures the distance that the car covered in that unit time, and looks like each of the car travels in a certain speed, and that's why the slope of the line is different, right? So let's start answering each one question after the other. So the first question is, which of the three is traveling the fastest? So if you see here, this is car A. Car A is this particular line. Car B is from here, and car C is this. So the slope, right? When we say slope, it is which line has a higher slope, right? Which one is steep, right? As you move from time zero, which one covers more distance per unit time? You can clearly see that the slope of B is actually the highest, right? It's the steepest, right? It's a steep mountain. If you consider this as a mountain, this mountain is a steep, so it climbs faster here, right? So which means that this car B covers more distance per unit time. So which means that car B is the fastest. Are all the three ever at the same point on the road? Let's see that, right? So see what will happen when they are all what does it mean when they are at the same point on the road? Which means that at some point in time they're all together, right? So which means that the distance that they would have covered at that point in time should be the same, right? Right. If three cars are at the same at the same point on the road, which means that they have covered the same distance at the same time, right? So which means that on a graph, all the three lines should actually intersect. But if you see here, not all the 3 points intersect. So you have this point where car B and car C has intersected, which means that both of them were at the same. They have covered the same distance at this particular point in time. At probably 0.8 time, the cars B and C were together. And here also you see that cars A and C were together at this point in time. Although they traveled at a different speed, but they somehow caught up and they were at the same position, same point here. And here is when you have cars A and B to have met. Right? There is no point in this whole graph wherein all the three lines intersect, which means that none of the cars actually were at the same point on the road at any time. How far has C traveled when B passes A? Right. So how do we find the moment when B passes A? For B to pass A, which means that B and A should have met at the same time, right? So which means that B, this is a line for B, and this is a line for A. So B and A have met here, right? So B and A has met here at time 1.2, approximately around 1 and 1.2 is when B has crossed A, right? Now, at this point, where was car C? Car C was somewhere here, right? So this is the path that car C had taken. So if you really see this, car C had covered a distance of, if you consider this point, it has covered a distance of 8 kilometers. But is it really 8 kilometers that car C has traveled? No, not really, because at time 0, car C did not really start from 8. It had actually started from 2 kilometers, right? So, which means that you have to reduce this 2 here. So, the distance actually traveled by C is from this point, which is 8 minus 2, which is actually 6 kilometers. How far has B traveled by the time it passes C? Right? So similar question. When did B pass C? So B has passed C at this point in time, right? The car B and C has met here. Now, car B has actually started from 0 only. So it is just sufficient that we find what this value is. So if you consider this value to be 5 or 6, right, which means that the car B has actually traveled, 5 or 6 kilometers by the time it has actually crossed C. Okay. Let's go on to the next problem. A ball is gently dropped from a height of 20 meters. If its velocity increases uniformly at the rate of 10 meters per second squared, with what velocity will it strike the ground? After what time will it strike the ground? So here again you can use the equation of motion. The ball is dropped from a height of 20, which means that initially before the ball was dropped, it was not moving at in a speed. So your initial velocity is going to be 0. The idea is to find the final velocity, and we see that it traveled. The height is 20 meters, so the distance is 20 meters, and your acceleration is 10 meters per second square. Now we know that we can use the third equation, which is primarily to calculate your final velocity. It is actually v square minus u square is equal to 2as. So in this case, u is 0. So v square is equal to 2as, and we can find that v to be equal to 20 meters per second. So when it hits the ground, it hits with 20 meters per second. So once you have v, you can actually calculate the time as well using the first equation, which is v is equal to u plus 80, and you can calculate the time to be 2 seconds before it hits the ground. Okay. So this is the speed time graph for a car, which is shown here, and how far does the car travel? And the question here is, how far does a car travel in the first 4 seconds? Shade the area on the graph that represents the distance traveled by the car during the period, and which part of the graph represents uniform motion of the car. Okay. So in the speed time graph, what does it mean when the speed is so what does it mean when the what does this graph say? Right? For every unit in time, up until probably at this point, right? Up until this point, the speed has actually increased, or the car is actually accelerated from here to this point in time. Right? The car has actually accelerated, which means that it has acquired additional velocity for every unit of time. Right? That is what has happened between 0 to this point. Now, to answer the first question, how far does the car travel in the first 4 seconds? So we know that when you capture on a speed time graph, the area under this particular line or the curve is what will give you the total distance or the magnitude of displacement, right, covered by that particular car. So in this case, your area is going to be from here till somewhere here, right? So this is the area that you're going to that will pretty much tell the distance traveled by the car in 4 seconds. So let me try to map that here. So somewhere here. Is the area, right? How far does the car travel in the 4 seconds? So if you are somehow able to capture or to calculate the area of this, then we should be able to say that the car has covered so much of distance in the first 4 seconds. Now, this is not a straight line, right? So this is a curve. So if I'm going to take this as an ellipse, right? So an ellipse is something like this. If you take this as an ellipse, now this part, and if the length of this is A and the length of this is B, so this is an ellipse, and we know that the overall area of that ellipse is pi AB, And in that, if you all what need is one quadrant of it, which is, pi AB by 4. So if I consider this to be 4 units and this one to be 6, then the total area of this ellipse is going to be pi times 4 times 6 by 4, which is going to be 6 pi. So this is the area of that ellipse, and this is the total distance covered by the car in the first 4 seconds. Now coming to the second part, which part of the graph represents the uniform motion of the car? It's very clear that, starting from here somewhere after 6 seconds, the car's speed does not change, which means that it is not accelerating. It is probably on cruise mode, and it is traveling at the same speed and every moment, and it's not acquiring any additional speed. So wherever this part is parallel, the graph is parallel to the x-axis, is when the car is actually traveling in a uniform motion. Let's go to the next one. Yeah. State which of the following situations are possible and give an example for each of this. An object with a constant acceleration but with zero velocity. Okay. So what this means is that the object has gone through a constant acceleration, but it has actually gone through but velocity is actually zero. So you typically think that your velocity acceleration is the rate of change of velocity, right? So as and when the object actually acquires or loses velocity at a certain rate, is what is called acceleration. Now think what this means is, you think about a scenario of typically when the velocity is actually zero. So if a car is moving at a certain speed, and when the velocity becomes zero, which means that the car has come to a full stop, and the acceleration is also zero after that, right? There is nothing the car has actually come to a stop. But think about a scenario of you're throwing a ball upwards, and the ball will tend to fall down. It will go to a certain height and it will tend to fall down, right? So which means that the gravity, the Earth's gravity, which we will learn about in the subsequent things, the pull that the ball experiences, right, towards the Earth. Now that gravity, the ball goes to a certain, you are throwing with a certain velocity, and until that velocity turns zero, the ball would then start to fall down, which means that the ball is undergoing an acceleration right from the moment you threw the ball up until the point it reaches a certain height, and then it then comes back. So it undergoes a constant acceleration in its entire path, starting from when you throw it up until a point, and then it once again hits back the ground. It undergoes a constant acceleration, but there is a moment in time wherein when the ball hits that maximum height, the velocity of that is going to be zero. It is only when it becomes zero that the velocity would turn negative and start to fall down. So that is a moment when there is a scenario where your acceleration is actually constant, starting from the moment when your ball is thrown and up until the ball falls back. But there is a moment in time wherein your velocity is going to be zero. So that is one example. The other example is a pendulum swing as well, right? So a pendulum is something like a pendulum is you think about a pendulum as it goes left to right, right? I'm trying to draw that here. There is a bit of a lag. So if you think about a pendulum typically goes from left to right, right? And there is a point in time when it goes to a certain end, and it turns back, right? So which means that the pendulum does undergo the same acceleration all throughout, but at the leftmost end as well as at the rightmost end, the pendulum will briefly stop, which means that the velocity of that pendulum is zero at that point in time. So these are examples wherein your velocity will be zero, but still the object is undergoing a constant acceleration. An object moving with an acceleration but with uniform speed. Okay, so this is an interesting thing. So what this means is that an object is moving with a certain acceleration, but the speed is uniform. So we learned that when the speed is when the speed is uniform, we learned that when a bus or a car is traveling with a uniform speed, it means that it is not accelerating. A bus that is traveling or with with a speed of 60 kilometers per second all the time, it means that it is actually not accelerating. It is not acquiring any new speed, right? Any new velocity or any new speed. So acceleration is all about the rate of change of velocity or speed, right? If the distance and displacement is the same, it is speed. So how can something really accelerate with an uniform speed? So that's an interesting scenario. You don't see that very often here, right? One possible example, which I think is valid here, is think about how the moon operates. The moon rotates around the Earth, right? The moon or any satellite. Moon is a natural satellite, so any satellite that we have rotates around the Earth, which means that it moves with a uniform speed, right? There's a uniform speed with which the moon is moving around the Earth, or any other satellite. But if you really think about it, the moon, why does the moon rotate around the Earth? We are going to learn about this in our subsequent chapters. But the crux of this is both moon and the Earth attract each other, right? That's called that's the law of gravitation, and both of them attract each other. But the moon is at a certain distance, wherein it is undergoing an acceleration, but it is still far away from Earth's gravity. So which means that it is at the right distance, wherein it only continues to fall. It continues to always fall, but Earth, because the Earth is also moving around the sun. Every time the moon tries to fall, the Earth takes that additional distance, moves because of its rotation, it creates that additional gap. And the moon, once again, by the time the moon fills that particular part, the Earth rotates and creates that additional gap. And it eventually, it so happens that the moon is always like trying to fall around the Earth, which means that the moon is constantly accelerating. But it is always and it is also moving with a uniform speed. It ends up with moving with a uniform speed around the Earth. So any satellite or moon would qualify for this particular scenario. An object moving around, moving in a certain direction with an acceleration in a particular direction. An object moving in a certain direction with an acceleration that is perpendicular to it. So I think a classic example here is an airplane. An airplane typically moves over the Earth. Think about the Earth's surface is parallel. The airplane moves parallel to the Earth, but the gravity is always going to be perpendicular. So which means that the acceleration is going to be always perpendicular to the airplane. So that's this example. So let's come back to the last one. An artificial satellite moving in a circular orbit of radius 42,250 kilometers. Calculate its speed if it takes 24 hours to revolve. So remember, the last concept that we learned as part of our whole motion chapter is an object that takes a circular path, right? So the distance. So here also the speed is going to be the total distance by time. So in this case, your total distance is the circumference, because the path is circular. It's going to be the circumference of that particular circle, and the radius here is the 42250. So which means that your speed is going to be 2 pi r, which is 2 pi 42250 over 24 hours. So which comes around to be 11065.48 kilometers per hour. So that's the speed of this artificial satellite. So I hope with this, we have completed the exercises, and I hope this was useful. So let me see you in another video where we will cover another concept in physics, and we'll go through the problems as well. Thanks.
One final thing before you leave. If you wish to revise the concepts that you've just learned, please look up and try out the free Revise app bot on Telegram app. Telegram is available for free on both iPhone and Android. Also, if you did like the content that you just watched, please do like, share, and subscribe this with your friends. Thank you.